As we continue with our today's insightful discussions, our next session dwells into the power of knowing automation, flexibility, and autonomy as a pathway to next-gen testing. This session will explore how cutting-edge automation and flexible testing processes can enhance the next generation of testing. So let's welcome Alan Merrick, Director of Testing Engineering at MSI DFATz Services.
Good morning. So this is direct field acoustic testing. This is talking about then the research and things we do for preparations for each one of our customers. Here we go. So we'll do a little short history, and then we'll talk about some of our setups that we do and the analysis and stuff we do in-house for them. And then we have some new analysis requirements that have come up from launch vehicle providers. So we started back in 1999. We were asked to do some acoustic testing for a company who did not have a reverberant chamber to test in. That's been the only way to do it before. So the early days up to 2014, it was a single input, well actually a multiple input, multiple microphones with one single drive output. Basically like a shaker control system, had multiple microphones instead of multiple accelerometers. Then when 2015, that was kind of discovered that was a bad thing. It had a lot of standing waves and issues in the acoustic field. So we went to a MIMO, multiple input, multiple output. And that did a whole lot of improvement for it. And that was a square, so you had multiple, up to 15 drives with 15 microphones controlling each of the drives. Then later we went into a rectangular control, so now we can do up to 24 microphones and we can do any number of drives that we wish to have. So every spectrum we do for our customers, we can test out in-house. We do a lot of development of the control system in-house as well. So we've done small satellites now, have been fairly new. 4 years now, where we've been doing small satellites, and then we increase the sizes up in the speakers in our 4x4, which is 4 set of subs and 4 set of mid-high, and then 6x6, 8x8, and 10x10. We've actually gone up 60 feet tall now. So the 4x4, the typical spectrums of the smaller satellites are less than 140 decibels. So these are small satellites. These are only 4 speakers tall for the subs, which is like 8 feet. So with that, we've done 16 microphones to do the development on this. We built a little simulator, which was our plywood box. Most of the time we do any kind of testing, we always start with a simulator just to make sure that we account for the absorption of the satellite when we set up a system. So this was done with 16 control microphones and just 4 drives coming out. So we optimize the drive functions, make sure the spectrum is met, and we actually did a rotation. We had accelerometers on the panels of the box just to see that the diffuse field excited all the panels in each rotation. So the test results came out very good. We had overall spec of 137.5. We were within 0.3 dB of the overall reference. And the power band, like 200 to 1,000 hertz, we're within 1/10 of a dB. All the microphones are plus or minus 3 dB, which is the standard specification required from us from the MIL standard NASA handbook 7010. So this was the earlier versions of the MIMO. You can see the individual microphones here in the colored plot, and then just basic setup with all the microphones in the circle. So we went to a 6x6. This is a more recent test. So we do the annulus for the microphones. It's generally about 5 to 6 foot. This one's a little bit larger, it's 6.7 feet. So all the microphone spacing needs to be basically 3 feet away from anything, and then we vary the the distances so we don't get standing waves developed by the microphones. So all the average microphones were within 0.4 dB. It's a very, very tight test. Average control within 0.2 of a dB. Generally, you're allowed 1 dB plus or minus on the overall. In addition, this was designed for an earthquake zone 4, which is like California. So you can see the drawing actually has marks in between all the speakers, and that's bracing every 8 feet put together on the speakers, plus you have outriggers, and in the real tall cases, then we actually have weights on them as well, so we can withstand a bad earthquake. So in this case, we had a special accommodation. It was actually a telescope, so you needed a very clean environment at 10K. So they lowered down a octagonal tent down in between the middle of our circle, and we had to go and suit up, bunny suits with all the wraps and gloves and booties and everything on to get in for a 10K environment and go inside, set up the microphones, calibrate them all. There was careful consideration for this one. I had some big flat surfaces for part of the cold sensing module for the telescope. Wanted to make sure there were no reflections back from the sensors. There was some satellites I've done in the past where you got a large, 6 meter or something, or 4 meter satellite reflector dish. Sometimes, a few times, they faced out. And when that happens, you get some reflections back in, and you have to be careful where you put your microphones so you don't pick up some crazy amplitudes. We also do the complete configurations now in CAD, so we know exactly where everything is located ahead of time, get all the braces in between the speakers set up, proper lengths to carry all the right equipment. In this case, the customer actually asked to have a view of where the microphones were in respect to the satellite. So they gave us them off of the satellite. So you put all these microphones out in space and you get an orthogonal view, and you can't tell if you're looking at one that's up front, behind, or how far away it is. It looks like some of them are really close or really on top, but in fact it's just one on the other side. So we actually developed a line that went to the center of the satellite to show you exactly what surface it was impacting. I don't know what that graph's doing there in the middle of my page. So one of the advantages we have with direct field acoustics is that we can actually have better modal density for the lower frequencies. In a reverberant chamber, the lowest frequency you can test is generally defined by one that has 5 modes. If you have 5 modes, then you're going to have definitely places in there where you're going to have a node and a high point, because it's basically a standing wave in the reverberant chamber. So it's a little bit uneven distribution over the height of a satellite. Whereas with direct field acoustics, every single speaker all the way up is giving you that exact sound, so you get better distribution of your lower frequencies. The other advantage with the speakers is you have complete control over the whole frequency band. In reverberant chambers, your noise generators are generally limited in the frequencies they put out. So WAS 3000 will put out 600 hertz, and you control the rest of the field by distortion, by controlling the flow and the power going to the coils. You control how much distortion you get, and then you get a normal 3 dB roll-off from those points on. And there is one EPT 200 noise generator that actually can do 2200 hertz, but it's very, very low power, so it's very difficult to push much out in those higher frequencies. So the curve on the left then is a normal, they call a haystack curve, and it's basically a 3 dB roll-off from the power bands, and that's the kind of field that a reverberant chamber basically makes. The one on the right, you can see there's a big bump out there around 1,000 hertz, which is very difficult to do in an acoustic chamber. So with these, this is the only way you can get these more complex types of curves. So in this case, we wanted to have this big bump out there, and the red curve there is basically what our system was designed to do. So we were short in the area of those higher frequencies in this particular case. So we came up with a box that added in the high frequencies. So being a modular design, we have separate boxes for the subs, for the mids, and now we have a set of highs that we've added into it. And you can see that the top curve with the arrow on it is what that box was able to get us. So that gave us the spectrum we needed with the margin of safety as well. We had plenty of energy in that to do. I need some help here. There it is. So these are some of the other kind of configurations that people have asked us to do. You can see the brown line there is basically the normal curve we do. So all these other curves then require extra systems to be added into it. We actually had one of them that required us to do an 8-hour test. Now, initially we were only able to do 30 seconds at a time because the speakers would overheat. So we've got a new set of speakers that we designed in-house and built in-house. And we're now able to do the full 145 decibels for a full minute. But now we have a request. It's a little lower level, only 141 dB, but it's 4 hours, 8 hours, I should say. So we went through the testing in-house and measured, all the temperatures of the systems that were going on, and found that the amplifiers were the problem. They were going to overheat. So we came up with a way of cooling the amplifiers, and we were able to run them consistently then. The customer actually wound up only running 4 hours because he forgot one of the test units to bring. So the next morning they came back and brought in the other unit to do 4 hours of testing there. But we were able to complete 8 hours as required. So then we had another really odd one that we never expected, and that was 31 kilohertz. That gives you some interesting challenges because all your audio systems and your control systems are all for a human hearing, which is 20 kilohertz. So we had to come up with some unusual solutions. There are amplifiers, of course, that do go out in higher frequencies, and we wound up getting some little tiny ultrasonic speakers. It's really crazy, $1 a piece. So you could put quite a few of them out there to come up with the levels that you needed. So we added these in there, and we're able to meet the specification all the way out to 31 kilohertz. It was interesting to note that the way this has always been done in reverberant chambers is they just give it best effort. So as I said before, the noise generators don't have that good a frequency resolution. They don't have the capability of boosting out in power. So it gave them very wide tolerances at the high frequencies and accepted whatever they got out of it. Instead, we were able to come in and meet the spec and keep it very, very tight, within 3 dB all the way out to 31 kilohertz. So then we've got some other ones now. We've gone the other way, and we had to engineer up stuff to get taller. So we did a test in Silicon Valley. It's a very high earthquake area, and we needed to go 32 feet tall. Picture you have here is another test we did that was 40 feet tall. So this is 10 sets of subs and 10 sets of mid-high speakers for 60 feet. Those two guys there are over 6 foot tall. See kind of the magnitude of this. The other big problem with this kind of test is finding a place they can test it in. And there aren't very many buildings that are tall enough with a crane to be able to pick up the test article and the speaker stacks. So a lot of these tall, like rocket sections, are done horizontally, but you can't test them that way. So we actually did some research for one of the companies and came up with the idea of coming up with a huge tent system that we could set up out in the parking lot. Gets you a 100-foot tall tent. You could bring in a crane and we could set up the test and run it. Of course, all these speakers are basically come from the music industry. Although these are custom, they're still designed to the same standards, so they will withstand the weather too if it happens to be weather. But your satellites won't, so we'll never have to really worry about that part. So we've gone through helping with companies to define facilities, requirements, and come up with solutions to try and meet their needs. The latest thing that's come up, it's actually a couple of years now, has been the European handbooks for the launch vehicles. And they've added a new request or requirement in there. Of course, they all say they're required in a reverberant chamber, even though they all accept direct field acoustics. And they're saying that the volume of the chamber has to be sufficient that the applied acoustic field is diffuse. So that came up in the Vega launch manual, and then the Soyuz and Ariane 5 launch manuals also are requesting to have the field be diffuse. And this has not come up in any of the U.S. markets so far, and they don't have any definition of how you define whether it's diffuse or not. So we've always been doing uniformity, also called homogeneity. So our handbook here for NASA Handbook 7010 says that it wants to be within 3 dB. So you see here, this is a plus minus 6 dB, and in the third octave, all within the 3 dB. The Ariane 6 says it needs to be within the 3 dB for an octave plot, which even gives us more of a hands up, I should say. So we're actually even more within spec for that. So this gives you the uniformity of the field, but it doesn't tell you anything about how diffuse it is. So this is a sync squared function. And they've measured then from Cassini. So you have an ideal line there with the arrow going to it, and you have the measured lines there. And first one is the radial difference between different radial microphones, and the other one's being vertical, showing the vertical doesn't have the same diffusivity. And this is what it looks like if you're in a reverberant chamber. So the ideal curve is buried down in there, and you can see it rolls off with a high frequency. So then we go through the different controllers that we've used, and the first single drive output, you can see that we're pretty far off from the ideal sync curves. So then we have uncorrelated drive, which means that a bunch of individual microphones, individual drive functions go out, and you get an improvement from a single drive system. So then we've got the capability with our system then to control the coherence. And with 60% coherence, you can see you get still better than a single drive. Then when you get to the zero coherence, you get quite a bit more improvement again. So this doesn't quite get to the point of being a reverberant chamber, but it is pretty close to your sync function, and we actually have some that the lines that actually come in under the sync function. So very diffuse field. So one of the things we're considering doing is making an average out of these. This is a disputed thing of averaging coherences together. I think it makes a little more understandable curve than all the grassy plots we were just looking at. You can see the purple line is pretty horrible, it's way far down from 1. So this is taking 1 minus your sync function or your coherence and coming up with a line. And as you can see, just like the sync function shows, this function shows you in the purple that the single drive is pretty poor at making a diffuse field. So what these different curves are then, the blue one is the rectangular DFAT control, and the brown curve then okay. So the top one there, the reddish one, is the reverberant chamber. And so that's kind of the goal we're going after. So this is something we're proposing. We haven't gone through and got a full agreement in the industry on that. If anybody has any input on ideas on this thing, I'd love to hear about it. So we are continually improving our processes. We set up facilities around the nation, around the world now too. It takes us about a day to come in and set up a test. We do a simulator or a dry run, and then the next day we take the test article. So generally we can keep the test article test time down to just 1 day. So this is very good for schedule. It's very effective in cost. I know the company I work for, it cost twice the amount of a test just to ensure the shipping of a spacecraft. So it's a very effective and efficient way of performing acoustic testing. So this is my contact information. If you got anything, I'd love to hear from you. Thank you.
Thank you, Alan.